Hi everybody, it's Mrs. Casil, and I wanted to show you how to calculate the momentum of your two cars separately, find the total momentum before a collision, find the total momentum afterwards, and find the total change in momentum for your system. So we've got two different cars here. We've got a red car and we've got a blue car. And for all of these, we have mass and velocity. So when we're trying to find the momentum in a system, right, a couple things we remember. Momentum is equal to mass times velocity. We also know that the total momentum before collision, so the momentum before has to be equal to the momentum afterwards. That's what the conservation of momentum law says. And we're talking about the total. So we're going to add all the momentum before, and we can add all the momentum afterwards, and that will help us determine if this is true. This is how you can solve for the velocity of an object after a collision if you want to predict like what's going to happen. So here we go. I'm going to start right here with the scenario you're asked to do. I believe first is to have the blue car be at rest. I'm going to move it over a little bit just so I can see it a little better. I've got the red car going 5 meters per second in the positive direction. And I'm gonna make the blue car big. You know what? Everyone always starts left to right and makes the red car big. I'm gonna make the blue car big. So let's do a couple things here first. Let's find the momentum, and we're gonna analyze what's happening before the collision, and then we'll analyze what's happening after the collision. So I'm gonna start with before. So the red car, the mass of the red car is equal to 1 kilogram. The initial velocity, oops, it helps if I put V for velocity. The initial velocity of the red car is 5 meters per second. So if I want to find what the momentum for red, and I'm going to use again that I for initial, the initial momentum of the red car, I'm going to take its mass times velocity. So 1 kilogram times 5 meters per second equals 5 kilogram meters per second. That's the momentum of the red car before the collision. I'm going to do the same thing for the blue car. The mass of the blue car is 3 kilograms. The initial velocity of the blue car is 0 meters per second. That means the initial momentum of the blue car is its mass times velocity. 3 kilograms times 0 meters per second is 0 meters per 0. I gotta get my units right. 0 kilogram meters per second squared. 3 times 0, gotta love that. So that's the momentum before the collision. If I want to figure out what the total momentum before is, I'm going to add those two together. I'm going to add the momentum of the red car plus the momentum of the blue car. So I've got 5 kilogram meters per second plus 0 kilogram meters per second. So my total momentum before the collision, 5 plus 0 is 5 kilogram meters per second. So that's how I find the momentum before the collision. I'm going to go back over to my simulation now, and now I'm going to press the play button. We're going to see what happens. In it goes, kaplamo, bonk. They've bounced off each other. This is an elastic collision where all of the momentum is conserved. So the total momentum now has to be equal to the total momentum before the collision. The car's individual momentum changed, but the system did not. So let's double check this and find out if this is true. Dropping my pens. So I'm going to look for the momentum after the collision now. So we kind of do this before and after when you solve the momentum problem. My mass is the same, right? The mass of the cars did not change. But the velocity the final velocity of the red car, the VFred, did change. Look at what it says over the top of my red car. It's negative 2.5 meters per second now. Negative 2.5 meters per second. Got a negative number in there. That's important. I have to include that. The final momentum of the red car is mass times velocity, 1 kilogram times negative 2.5 meters per second. That equals negative 2.5 kilogram meters per second. That's the momentum after the collision for the red car. You'll notice it's less, right? It's a lot less. Negative 2.5. If your bank account said plus $5 million and the next day it said minus $2.5 million, you would have lost some monies. Where did the momentum go? It went into the blue car. So let's go check it out. Let's go see what the momentum of the blue car is now. The mass of the blue car. Again, the mass didn't change. It does in some types of collisions. It was 3 kilograms. But the final velocity of the blue car, it started at rest, but it got bonked and then it started moving. Let's go back and look at our simulation. 2.5 meters per second. 2.5 meters per second. That's a positive 2.5. So the final momentum of the blue car is mass times velocity, 3 kilograms times 2.5 meters per second equals, I got to do that one. That's a 5, and then there's a 1, and there's a 6, 7.5 kilogram meters per second. Okay. So this one gained a lot of momentum. Now is where we look at that system total. So if you were looking at what goes in your lab document, this number, this is the momentum before the collision. This was your system total before the collision. We're going to do that same thing right now for the total after the collision. Total momentum after. We're going to add the momentum final of the red car. Plus the momentum final of the blue car. We get negative 2.5 kilogram meters per second plus, and let me raise it up a little bit, plus positive 7.5 kilogram meters per second. I'm just adding them together. One of these is negative though, so when I add them together, you can use your calculator, you can use your mental math, you get an answer that is that the total momentum after the collision is positive 5 kilogram meters per second. What do you know? This is the whole point of the law of conservation of momentum. Up here, we have that the momentum before the collision is equal to the momentum after the collision. These should be equal. My highlighter doesn't write very brightly. These are equal. My little black pen doesn't write very brightly. And that's a G anyway. Equal. There's a Q. Yeah, you guys. Looking forward to it. Right? So this is how we show that momentum is conserved. I'm going to kind of highlight what were the steps I went through to solve this problem. So in summary, first thing I did is I analyzed the momentum before the collision separately from the momentum after the collision. I looked at each object separately. So first I found the momentum of the red car by taking its mass and its velocity before the collision, multiplying them to find its momentum. I did the same thing for the blue car. I took the blue car's mass and the blue car's velocity before the collision, multiplied them, and found the blue car's momentum. Then I added them together to find the system total momentum before the collision. I did the same exact process for after the collision. I looked at my simulation to find what the velocity after the collision would be. I did mass times final velocity for the red car, and I kept my negative sign in there to determine what the momentum was for the red car after the collision, and it was a negative number because it was going that way. The same thing for the blue car. The mass of the blue car times its velocity after the collision, multiplied them to find its momentum. To find the system total, I added together the red car and the blue car's momentum after the collision, and I got 5 kilogram meters per second, the same as